In a previous video, we introduced this closed loop feedback control diagram as illustrating a concept that may be familiar on how error is used to drive a controller based on feedback through a sensor. And of interest is controlling the plant or the process of interest, right? So we've discussed this before. This is the plant here, the controller, and the sensor. It's good to be familiar with these concepts in general. And this is basically a nice graphical representation and easy to remember, and illustrates how we implement PID control. And this lab really is more so than maybe a course on control, interested in showing you how to close the loop and build a controller and how to test it. And we will talk a little bit about the theory of that, but really mostly we're focused on implementation. It is good to discuss why we close the loop as opposed to open loop control, which was discussed in the first video. The advantage of closed loop control is that if you do have disturbances, in your system, it is meant to reject those disturbances. It can try to keep your variable, the output from your plant that you're interested in controlling, or the control variable. It can keep it on track, even if you have some external disturbances that you haven't accounted for in your modeling and in your analysis. You can also, with a controller, reduce how sensitive it is to changes in the model parameters. So we talked about how with an open loop controller, you would specify some reference in order to achieve a desired output by just using an open loop gain. Again, there's more sophisticated ways of doing open loop control, but that's the basic idea. But this gain here is based on your model understanding of the system. If there are some things that change here and this G is not exactly the G you thought, then obviously there's going to be some error in your output. Closed loop control is meant to reduce how sensitive your controller will be output to parameter variations. You can also implement tracking of the reference input instead of just having, and you can think about different, on the input side of that controller, here's your error, here's the feedback coming from your measurement, and here's the reference. Sometimes we talk about if the reference is just constant, or you're trying to regulate something, we call it a regulator. Say you're trying to keep it at zero, but R might also be changing. You might be trying to track something, so you can do that now with feedback control. Also, it turns out that when you close the loop, you actually change the performance of your system. You can change how your system performs, and that's at a cost, right? Because you are, and I'll show that later in the diagram. You're putting power into the system, and you're changing the system effectively by closing the loop. And so, in fact, that points to one of the disadvantages is whereas if you have an open loop control system and you know that you've studied it, it's not unstable, and you're just putting inputs and it's tracking it, the worst that can happen is you're off. But generally, you can't make that system go unstable, right? By closing the loop, because you can change the system, basically the characteristic equation, right? You can change the poles of the system. You can make it unstable based on what you do to it with the controller. So that's one of the disadvantages, is that you do have to be careful. Sometimes you can tune the control system and make it work, but only through more detailed analysis and study can you make sure that you avoid bad behavior. So that's one of the disadvantages. It's one of the costs of closing the loop, aside from the fact that you need an actuator and you need a sensor and so on. Again, you may require tuning and model design, model selection design in order to complete that. But again, it all depends on the design decisions that you're making. A little bit, some of these points can be more clearly made by looking at sort of a more theoretical basis for the feedback control diagram, where I've now put in some transfer functions. So now think of these as transfer functions like you might have studied in a course on dynamic systems. And you can actually solve, right, through the block diagram algebra for this output C as a function of the input. So what are the inputs here? The inputs are, of course, the arrows that are coming in here and here. So there's only two inputs on this system, the reference input, which you have control over, and then you don't have control over disturbances, but that's an input. So note there's an input here from disturbance and an input from reference, and this is the output of that whole system. But note that the transfer, there's two transfer functions that relate each of the inputs to the output. But note also that the transfer functions that describe the denominator in those transfer functions are the same as it should be. And so what you're changing now, this is your original system. What you're adding is this and this here. So that's how you can change the behavior of the system. And that's what you do in a controls course, is figure out, hey, how do I select GC? How do I select H in order to get the kind of performance I want? In turn, since if you recognize this as a transfer function and the denominator is the characteristic equation, this does determine the poles of the system, right? So if you think back to, if you get poles on the right hand side, it can go unstable. So you want to select poles that are going to give you good performance, etc., right? And keep it stable. All right, so that's kind of a big picture. What we want to focus on is how do we build a controller without maybe going into all that theory. And we're going to focus on implementing. You can implement a lot of different kind of controllers, but on, off, and so on. Obviously, we already talked about open loop, but we're talking about PID and the three types of actions that are in a PID controller. And obviously, those are proportional, derivative, and integral. Well, proportional, integral, and derivative PID. Right. So as each indicates, right, the proportional control is I'm going to have an action UP that's proportional to error. So that proportion, the term that's used that relates to what kind of action is it generating, and it's an action based on error, right? Remember what we're doing is taking the error and putting it through this controller, and we're trying to generate this total action here. And so it's based on the input of that controller, which is the error. So here, error is proportionally acting to give you UP. In this one, I'm integrating error over time. In this one, I'm taking the derivative of the error, and that forms your total action. And PID, you're using all three. Sometimes you have just a P controller. Sometimes you might just have a PI controller. And sometimes you might have a PD controller. It all depends. And of course, sometimes you might use all three. All right, so different combinations. I'll talk a little bit more about how you implement this in other ways. But because we are doing this on an Arduino, it's going to be a digital implementation. And it's common. And if you go look up in the textbook in digital control, some standard representations for how do you write. And so a digital controller is an algorithm. It's code. You're going to write it in directly into C code, for example, on an Arduino. And so you can see you're just making calculations. So instead of so this error now is a line of code, right? It's calling the X here as the variable, like the process variable that you're trying to control. R is the reference, and the K represents, think of it as the iteration variable, because remember, you're implementing this on a computer, so it's important every time your computer makes a loop, like a while loop, like we build in an Arduino. The little control loop in Arduino is always running continuously, and every time it goes through the loop, it computes on a kth iteration, right? Each of these terms. So first you've measured something, take the difference, and that gives you the error, and then you just perform your actions, your relations on each of those. Digitally, these are very common. It's easy to implement proportional. You have a constant KP, a gain that you found works well. And again, sometimes you have to do this experimentally. Sometimes if you take a controls course, you look at ways to come up with these gains theoretically through different kinds of analyses. In the lab, we'll mostly try to show you sort of empirical ways to tune the controller. Tuning the controller means finding KP, for some reason can't get the order right, KP, KI, and KD, right? How do we find those? Tuning refers to finding those values. And you can see that the algorithms are pretty standard. Actually, you've often thought of an integral. If you discretize that, you have the time step in there. But it's actually pretty more common if you look in some reference text that you don't even take into account the dt in there. Note that there's no delta t. You take the difference between the current time error and this step, and you keep the previous one, and you divide it by, you do an approximation, multiply it by the gain. The derivative also, you don't even use the error, you actually look at the difference. So again, this is just one way from one textbook that I'm showing you. It's a classic book by Ostrom and Widmark. So I kind of like that. It's a book on PID controllers, very standard book. And then once you get those three actions, you have this. I've also seen this implemented in a lot of other different kinds of software. There's reasons for doing this, and I want to discuss that because in the lab we do take into account the delta t, and I'm going to talk about why we can do that. So in a digital implementation, again, this is just my perspective here. In this digital implementation that you might see, the time step may not be explicitly used, but you might run across in your work algorithms that look that way when you're looking at the integral and derivative terms, right? You don't need it for the proportional. But you can think about that the delta t is implicit because, the gains are going to be what give you good performance. And so what time step you're taking, how long that control loop takes. So the delta t is always implicit, even if it's not in the calculations. Now, one reason I think that you don't often see it in some implementations is because, well, you don't need it. You can integrate the delta t right into the gain. If you're going to tune it anyway, just let the k absorb it. And sometimes, if you have really fast microcontrollers, those delta t's can be really small numbers, right? Microseconds and so on. So you can avoid getting really small numbers if you have very small delta t's by just ignoring the delta t because you don't really need it. Let the k compensate for it, right? So on some micro, you might have finite word length issues, and you might want to do away with the delta t. For our implementation on Arduino, we actually are running pretty slow. The delta t is actually on the order of tens of milliseconds, so the delta t is not too small. We went ahead and we're including it in these PID terms. Again, one subtle advantage is that when you look at the gains of the k's, it could be related to what you might do in a theoretical analysis. Since we're not doing theoretical analysis in this lab, that doesn't make a big difference. So really, in my opinion, you could go either way and either leave out the delta t or leave the delta t in. It just happens that in this latest version for our controller, we have it in there. By the way, if you did leave out the delta t, then the gains would all have the same units. And whereas if you include the delta t, then the gains have different units based on what u is. Remember, each of these, and you can do the analysis and show what the units of the k should be. Okay. Now moving on to, as we've discussed, right, the controller, the practical implementation. You've got error coming in and you've got u going out, and what we want, is we want an output that's going to be related to whatever's going to go into the plant, right? So whatever that plant needs, u has to be the same unit. So I'm showing an example here. I have a little controller here that's measuring position of this mass, and the output from this controller is going to have to be force. If I'm trying to control position, then my transfer function is going to look something like x over f. So if my g has units of, right, let's say inches over pounds force, and if I'm going to go for some reason with English units, then obviously I'm going to multiply it by pound. So my u has to have units of pounds force, right, or newtons, right? I should have stayed with SI to begin with. But in any case, you want to make sure that that's consistent, right? So your gains are going to be consistent. And it's kind of subtle, but sometimes when you're doing theoretical analysis, that controller, it doesn't show the units of it. If you think about it, the whole system includes the actuator. So really, this signal here is some other unit, but by the time it comes out, it's forces. A little bit subtle, but I'm going to show you how that works out in in some other examples, and hopefully that'll make some sense. Again, what we need is pulse width modulation for this little motor. And so let me show you, like for the motor speed controller, we're going to need as an output, right? We want to have something here that generates pulse width modulation. We have error coming in, and we want to get pulse width modulation in our controller equations, right? So what does that control diagram look like? And it might help to kind of just draw that out. So we know that our plant is our PMDC, right? Motor. And the output, strictly speaking, is speed. And if we want to show it kind of in a classical way, we might feedback and go ahead and draw a little block here that says encoder, right? Because then that encoder gives us a measurement. We're doing some processing on that, so really the output is also, so we could say that, oh, this is the motor speed, and this is actually, and we put a little tilde there, that's the measured or estimated speed. By the way, I'm showing this with kind of continuous time signals, but we know that all this is discrete time, isn't it? So over here somewhere, we're going to be giving it a reference, and that same units is here, so we're going to have an omega m, and we call that omega m ref. You can designate that. And by the way, that's a plus always, and this is a negative. We always use negative feedback. Positive feedback can be destabilizing. You can read more about that somewhere else, or if you take a controls course, you can show why negative feedback is stabilizing, positive feedback is destabilizing, and so that's how we're going to generate some error. Again, these are all discrete signals. We're computing this in an algorithm, but we're showing it at continuous time. And a lot of times we do analysis in continuous time, and then you can also do analysis in discrete time. Again, that's a little bit more advanced, different formulations, but this is still a very helpful formulation. It's the same. Again, the signals may just be discrete time. So we're going to take that error now, and we're going to go right into, as we said, a PID algorithm, because that PID algorithm is going to generate for us a pulse width modulation. So that what's coming out of that is the pulse width modulation. But pulse width modulation doesn't go into the motor, does it? It goes right into, let's put a little block here that represents the H bridge. And then that H bridge sends power, doesn't it? And I'm going to show that, which is, even though we know it's a power signal, like in a bond graph, we can show that with a power bond, but we are sending here some, equivalent voltage, right? And we could show up here that we have voltage coming in from the battery. See that? So I like to think about how this right here is kind of signal level stuff. Even this is signal level. But the power, I'll show that with a big arrow here, right, is coming from up here. You have a battery or power source up there. And so basically, again, this power modulation is telling this power how to flow into that motor. So this is what your feedback control looks like when you then go build it, okay? And this can be very useful to kind of sketch things out this way so you can see where's signal, where's power, because they are different. And when you build them, remember when we built the drive for the motor, you had the H bridge, which brings power from your power source. But then the Arduino is low power, right? So you don't want to mix those up. There's two different levels of power. One signal, sensors are signal level. Power is the oomph, right, is what makes things happen. All right, so finally let's add a little bit of, turns out you can add another form of control so that the total control action could be not only what you base on error, but also if you know a little bit about your system, you can add a little bit of what we call feed forward. So this, we could use our open loop control. Turns out this can be very helpful because if this is reasonably good, then this error path has less work to do, if you want to think about it that way. So the total control action is a feed forward part plus the PID, which is an error-based part. Okay, and so we'll show you how you can implement, and you can actually turn them on and off in your digital controller and say, hey, what if I don't put any feed forward? And you can see that maybe the PID struggles a little bit. When you put in the feed forward, it helps it. And it's really good to be aware of the fact that you can help things along a little bit. Let the feed forward do the heavy lifting, as I like to say. Okay. Just to give you a little bit better sense maybe of just implementation, I like to use this classical cruise control example. Everyone's familiar with. It's a speed control, just like what we're doing in the lab. And here's your feedback control system. You're measuring speed from a speed sensor, say based on the wheel, and there's an engine drive which incorporates the vehicle and so on. And there's in this class, this is an example from quite a bit ago, 1982, but I still like it. It shows a throttle actuator that's driving an engine. So here's your actuator and plant. Here's your sensor, which you could put in the feedback path. And then here's the control electronics, right? And there's a commanded speed, which we all know how cruise control works. And I like this example from this book by Ribbons because he breaks it up. This was the first time I ever saw this when I was a student, and I really liked it. Shows how the error, you break it up into two pieces like we just discussed. In this one, he's building a PI controller, very classical. Turns out PI control is really good for, reducing error. The integral part, think about the integral as kind of looking at the error all the time, and it's trying to reduce that error. So if you've got a difference in speed, it's going to kind of bring the error down to zero. Okay, you can look up these, what each of these factors does. The proportional can help you reduce error, but the integral especially helps you reduce error, but it can start introducing a little bit of instability because of the way it changes the dynamics, right? Finally, derivative control, which is not included here, is really good for like adding damping to the system. You look back at the slide where I introduced the three terms. I didn't go over it, but it talks a little bit about each of these effects of each of these. The derivative term, think of it as almost like adding some damping. And remember, derivative is like looking at the rate of change of error. So it kind of is anticipatory, and it can add a damping effect in your system. As it's kind of a very simplistic way to look at it, but that's effectively what it does. Error, integral, nice for bringing down your error. Derivative, nice for damping out the response. So when you're tuning, if you see a lot of oscillation, add some damping. Take away a little bit of the integral. If you're seeing that you've got too much error in the steady state, add a little bit more integral. All right. Proportional tends to make things work a little faster too. All right. Derivative can help with that too. All right. So going back to this, I kind of like how it's showing that the control signal that's going to the throttle is a sum of these two things. And I like that because the way Ribbons did in another illustration in his book is he showed, and this is those of us who have studied electronics, you can build this controller with analog circuits. If you've studied circuits, you can build a proportional amplifier, like a proportional gain with an op amp. You can build a summer with a summing amplifier. You can build an integrator with an integrating amplifier. And you can also build an error amplifier with an op amp. So I kind of like that because it shows that if you had to build this with analog electronics, and by the way, these used to also be built with fluid circuits as well, because the circuit concepts are the same. So you don't have to do this digitally. It just happens that nowadays it's so easy for us to build modern electronic controllers on an Arduino or on a microcontroller, and that's really the most common way. But it doesn't always give us, it hasn't always been that way, and you still will find some analog controllers out there, even physical controllers that have the same kind of functionality. So I kind of like to kind of show you this. The other thing I wanted to show that's related from this example, last part from this, is that the throttle is very similar to the H-bridge. What it does, what you're doing with that is you're sending a pulsing in here, and you're pulsing this thing on and off, and look how it's using power from the vacuum jet, from the intake manifold to drive the throttle actuator, right? So here's the power, and then here's the signal, very similar to kind of an H-bridge. So you're kind of pulsing it on and off in order to kind of adjust your throttle, and that's how the actuation works. So it's kind of nice to look at how some of these can be related. I hope you find that interesting. Finally, just closing the loop back to our drive, power through here, and again we're modulating with pulse width modulation. So the key thing is, and so it's interesting to think about it this way, that the error path and the modulation path and all that is is to generate pulse width modulation, and that's what gives us our control voltage. Coming back down to implementation, when you go to the lab, we're going to give you an Arduino code that shows you how these functions are not implemented in circuits, but are in fact, right, written simply in code, as you might anticipate. So you can see how, actually the code that will give you is going to allow you to experiment with open loop and closed loop together. So here's the case for open loop where I just have open loop gain times the reference, and that's like the open loop controller we discussed in the previous video. But now if you choose closed loop, right, and you can, the TA will show you how to use the Python code to send Arduino command, say, hey, I want you to run closed loop control, and then it'll start choosing this case. And in each of these steps, now remember, this shows this loop that's running in Arduino every time step, every delta t, right? Every delta t, it finds a delta t, puts it into the proper seconds, and note how it's using delta. This is a term called EDT, which takes the error computed here, multiplies it by the delta t in time, and starts summing that guy, and that's your integral term. Here's your DEDT, which it just takes the difference between the current and the last divided by delta t. Remember, this is where you could get into trouble if those delta t's are really small, because then you could get spikes here. There's noise, by the way, noise in the signal also. Delta t is notorious. Derivative control is notorious for introducing noise, so you have to be careful taking these approximate derivatives when you're putting in a derivative control. Sometimes what's done is that this guy right here is put through a low-pass filter in a digital context to smooth out that noise. Lastly, when you implement your pulse width modulation, here's the feed-forward part, or the open loop part, and then here's your PID. Right? And by the way, by just selecting, if you decide you just want a PI controller, you just make KD equal to 0, right? If you want a PD controller, make I equal to 0. And then, of course, you can tune these by playing around with KP, KI, and KD. And, of course, the OL gain, the open loop gain, comes from your approximation, but you could also tune that to get better performance based on your model approximation. Finally, we can test our designs and experiments and so on. And we're also going to give you a simulation, of course. Got to do a simulation of the closed loop control, show you how that's implemented in Python. I think very empowering to be able to go just into a nice little Python simulation and play around with feedback control. It's so easy to implement, so easy to kind of get some insight into, hey, what happens if I change these gains? You could walk into the lab and already have an idea of what's going to work, what's not going to work, if you have a reasonably good model, right? And you've got that with this little motor. Just to show you the gain, the code looks very much the same. You're going to be able to download this code. I'm showing here that it's using the open loop is using the torque speed curve, but up here you can select in your simulation. Oh, I want to use the open loop gain from my correlation, or I can, there's option 1 or option 2, or you can use the torque speed curve. And then here, right, there's a PID part, and then you add them together, and then there's some scaling that's done here in order to get the simulation to run the right way. The key thing and I'm not showing the whole code here, but there's a loop that's running, and maybe what I'll do is just jump right into that code. It's right here. So there are all the parameters like you'll have. You set the delta time, and then you're going to start this, what I call the big loop, which is here. And this loop is going to run just the way Arduino runs, right? And so what it does is it computes all the terms, computes the sums, the delta t's, and here's what I was just showing you, the snippet. But then what it does is at each delta t, it then runs into a little RK4 simulation. And so over that delta t, it integrates using RK4. It gives you just a little bit more, and what it does is see how it computes the voltage that is equivalent from your H bridge, and it sends that to the motor. And the motor just says, okay, you're giving me this voltage, I'm going to do something, I'm going to move. And whatever the motor's driving, you could include that in the model, and then you just continue, then you end that simulation, you just take the last values here. This is just recording the last values, and then you start those and you use them as initial conditions in the next time step. By doing this, what I call big loop, if you study it, it's very similar to what Arduino is doing, right? Arduino is at every time step, it's setting every delta t. Within every delta t, it's computing all the control stuff, and then it's sending out a voltage, and that voltage is out there. It's not going to change until it comes back and recomputes new ones. So over that delta t time, approximately, the motor's doing something based on the delta t. It's not changing. It's based on the last pulse width modulation command you sent it. So it's very close to what we're simulating here. So again, as we did for open loop control, we can simulate the feedback control. I think, again, very empowering type of tool for you to have going forward. And you can always come back and look at it later if you ever have to study control. If you might take a controls class, hopefully it gets you ready for that. In any case, the idea is in this lab, look at how to build a PID controller. What does it look like? You'll be able to see that, hey, with open loop control, you can't make that thing unstable. But once you close the loop, you can start playing with those gains, and you could possibly make that little motor act weird. It starts kind of going unstable. So just being able to see that, how tuning those 4 parameters, if you think about the open loop gain, can really change the behavior of the system. I think hopefully will give you a good insight and you get a good experience. All right.